thanks for the introduction. So my purpose today is to talk about quantum technologies, what they can do, how far are we with building them, and what impact they would have on the field of IT security, which is one of the big future applications for quantum technologies when they are ready. So quantum mechanics is a part of physics that studies laws of nature on the level of atoms and molecules. And quantum computing and quantum technologies are concerned with using quantum physics to solve different problems in computing and information processing. So here is one very simple example for which I can explain how it works. So one of basic principles of quantum physics is that measuring a quantum state changes the state that is being measured. So think of a particle in a magnetic field. This particle will either fly to one side of a magnet or to another side of a magnet. So inside of it, it has some property called spin, which decides which direction it goes. And this spin can be pointing upwards or downwards, or it can be pointing sideways. And in that case, there is some probability that particle will fly to one end of the magnet, and some probability that it will fly to the other end of the magnet. And once this has happened, the state of particle has changed. If it flew upwards, it is now pointing upwards. If it flew downwards, it is now pointing downwards. The original state of the particle no longer exists. Instead, this particle is in one of these two states, up or down. And we can actually use this for secure data transmission. So think of two parties that are connected by a cable, and someone in the middle might be listening to them. And if these two parties can communicate quantum particles, one side can send the other side a sequence of particles in different states. For example, those could be particles of light or photons polarized in different ways. And then if someone in the middle is listening to them and measuring these particles, he's disturbing the particles by measuring them. So the two parties can use some of these particles to check if someone in the middle is listening or not. And if this test is successful, if they detect that nobody is listening, they can be safe. They know that they have this communication channel just to themselves, and there is nobody else. And then they can use the remaining particles to generate a secret key. This secret key is known to the two of them, and is not known to anyone else. And then they can do secure communication. Once two parties have secret key that they know and nobody else in the world does, they can communicate securely using one of the many schemes that we have. And what is interesting here is that this is a scheme for secure communication that is unconditionally secure. For most of classical cryptography, it is secure under some assumption. There is some code-breaking task about which we think that this task is hard to solve, but we don't know that. In the quantum case, we can prove that these schemes are secure by using just the basic principles of quantum mechanics. So this is secure unless quantum physics is wrong. And this is a very strong guarantee of security. Now, the other thing that we can do with quantum states is quantum computing. We can encode information into quantum states, for example, 0 in a particle that is pointing upwards, and 1 into a particle that is pointing downwards. And then we can compute by manipulating quantum states. And for some tasks, this can be much faster than conventional computing. And here are 3 examples, one of which is very relevant to security. So, well, first, the task that is usually thought as the killer application for quantum computers. So that's simulating physics. So here is an almost 100-year-old quote from one of famous physicists of early 20th century. At that time, he said that the underlying physical laws for a large part of physics and whole chemistry are completely known. And the only open problem is that if we try to apply those laws, the equations that we get are too complex to solve. So we can write equations, but we cannot solve. And now, almost 90 years later, the situation is still the same. We can write equations, we cannot solve them, even on the fastest supercomputers that we have now. So, one of the biggest applications for quantum computer would be simulating quantum physics and chemistry. If we have a chemical molecule, we can describe it by equations of quantum physics, and then we can model the behavior of this molecule by simulating it on quantum computer. So right now, it's done on supercomputers. About 10% of supercomputer time is simulating chemistry. So quantum computers would be able to do it much faster and much more precisely. Now, here is the second application. Let's say that we have a number that is a product of 2 large numbers, and we are given this large number, and we want to factor it into 2 smaller numbers. And then for large numbers, this is a very well-known difficult task for ordinary computers. If we build quantum computers, we would be able to solve it much faster. And this is the one that is relevant to the IT security. If we look at today's public key cryptography that is used for security of communication all over internet, the security of public key cryptography depends on the fact that factoring large numbers is hard. Code breaking roughly corresponds to factoring. If we could factor large numbers, we could break the most frequently used encryption schemes, and we would be able to read a very large fraction of the information that is communicated over the internet. And the third big application of quantum computers is searching large amounts of data. Let's say that we have some large number of objects, and we want to find an object with a certain property. And the only operation that we can do is checking these objects one by one. Then, so we check this object, we see that it's not the right one. Then we check this object, well, we see that it's the right one. And if there is one object to be found, and there is 1 million of them, then on an ordinary computer, we would pretty much have to check all the 1 million objects. But if we had a quantum computer with quantum access to these objects, we would be able to search among them in time that is roughly square root of the number of objects. So here is a popular example. Let's say that we have a phone book, and we want to search for a person with a certain phone number. And the phone book is ordered by names of people and not by numbers. So the only thing that we can ordinarily do would be to go through this phone book and to see who has this number. And if there is 1 million phone numbers in this phone book, we might have to check all 1 million before we find this phone number. But if we had this phone book in a memory of a quantum computer, we would be able to search it in time that is square root of 1 million phone numbers, 1,000. And the thing applies to any task that involves searching among large number of possibilities. If we have to search among 1 million possibilities, we could do it on a quantum computer in time 1000 instead of 1 million. And that is also applicable to IT security, because this phone book that we could be searching could be some task that comes up in breaking ciphers. So if at some point to break a cipher we have to search among 1 million possibilities, a quantum computer would enable to do the same task by just checking 1000 possibilities. Okay, so these are the main things that quantum technologies can do for you. Now, how far are we with building them? So quantum key distribution is quite far moving into the practice. There are several commercially available systems for quantum key distribution boxes. One can buy them and do quantum communication over an optical cable over distances of 20 or 100 kilometers. And the first deployment of quantum cryptography was in Boston area in 2003, and the first commercial deployment was by Siemens in Netherlands to create a secure quantum link between two of their data centers in Netherlands. An object of ongoing research is how do you do secure quantum communication over larger distances. So if you want to connect several of those systems together to communicate over large distances, then you need something in the middle, you need quantum repeaters. So the question is, how do you do them securely? And another possibility is quantum communication over air and quantum communication over satellites. So just a few weeks ago, China launched a quantum space satellite, and what they plan to do is a secure quantum communication through space. So the satellite would communicate to two parties on Earth, and these two parties would then have a secure secret key that they know and nobody else does. The first stage of this experiment is creating a secure quantum link between two places in China. The ultimate goal is to have an experiment of creating a secure quantum link between Beijing in China and Vienna in Austria. And quantum cryptography through satellites is actually quite interesting possibility. There have already been experiments with quantum cryptography over air, where people would send signals over air from one station on Earth to another station on Earth over distances of 50 or 100 kilometers. If you use satellites, you can achieve much bigger distances, and communicating to a satellite is not that difficult because there is only about 20 kilometers of atmosphere over us, and once the signal gets through these 20 kilometers, there is no air and there is nothing where this signal might get lost. And now on from quantum key distribution to quantum computing. So building a quantum computer is essentially a big research project that will take multiple decades. It has already taken about 20 years. I expect it to take 20 more years. So interesting thing about quantum computers is that at the core of quantum computers there is this functionality of a quantum bit, a quantum particle that encodes information. And then there are many physical systems that one can use to implement this basic functionality. And these physical systems all look very different, but they can all encode information and they can all do computation. So there is at least 10 different physical ways how one could build quantum computer. And then for each of them, there are steps through which one has to go towards building a quantum computer. It starts with operations on single particles, then it goes to algorithms involving multiple particles, and then it goes to quantum error correction. For any way to build quantum computer, the operations that we do are going to be imperfect, there will be noise, so there will be error correction necessary. And one of the experimentalists involved in building quantum computers, Robert Schoelkopf at Yale University, he has divided the path towards quantum computer into 7 big steps, 7 milestones. So at the moment, the world is at milestone 4. The first 3 have been completed, the 4th one is halfway through. And these first 3.5 milestones have taken 20 years. So it's reasonable to think that the remaining 3.5 would also take 20 years or so. And so here is a technology that is now the most promising one for quantum computers. It's superconductors. Superconductors are materials that conduct electricity with no resistance if you cool them down to a very low temperature. And superconductivity is a quantum effect. What happens is that a large number of electrons in a superconductor form one very big quantum state. And then this big quantum state can flow through the superconductor with no resistance. And then we can encode information into this state. For example, encode 0 in an electric current that flows in one direction, and 1 into electric current that flows in the other direction. And then scientists at UC Santa Barbara have been able to do quantum operations on superconducting quantum bits with precision 99.9%. And another thing that is interesting about these superconducting quantum computers is that elements for them look just like conventional logical circuits that are inside of our ordinary computers and our ordinary cell phones. There are slightly different materials, but these quantum computers look very much like chips of ordinary computers. So one can microfabricate them using the methods for classical electronics. And this is very promising because on one hand we can do a high precision quantum computing. On the other hand, once we do a few of those quantum elements, we can then fabricate them in large amounts using the same methods that computer industry already does. And this has created a lot of interest in building quantum computers from industry. So the group that did these experiments with superconducting quantum bits are now partners with Google. Google is funding their work, and many of their researchers are now at Google. And their purpose is to build a quantum computer for artificial intelligence tasks that Google is interested. Intel has invested $50 million in Delft University of Technology in Netherlands. And similar investments from companies are happening in other places, including China. So suddenly, with these advances in building quantum computer, there is a lot of interest from industry, and there are actually companies that are willing to invest tens of millions into possibly building a quantum computer. Either established companies, or there are quantum computing startups which are gathering tens of millions from venture capitalists and investors to build a quantum computer. So quantum computing is moving from research projects that involve one professor and 3, 5, or 10 students to large projects that involve companies and that have building a sufficiently big quantum computer as their purpose. Okay, so what are the perspectives? I think there are multiple goals that we can set for quantum computers. The closest goal is to build a quantum computer that is impossible to model on an ordinary computer. So that would be a quantum computer that does not necessarily do anything useful, but that is complicated enough so that we cannot model it on an ordinary computer. Next step would be quantum computer that solves some useful task. And then third step would be quantum computer that breaks today's encryption schemes like RSA or Diffie-Hellman. So the first stage, quantum computer that is big enough so that one cannot simulate it on an ordinary computer, is actually quite close. Google is working on that. They are putting the time at 1 to 2 years. So what one would need is about 50 quantum bits, possibly noisy quantum bits. That's the point at which quantum computers get complicated enough so that they can no longer be modeled on an ordinary computer. The next stage after that would be to make a quantum computer solve something useful. Probably the first useful tasks will involve modeling quantum physics and quantum chemistry. And that would require going to 200 or 500 quantum bits, and also having some form of error correction on these quantum bits. And then the third stage would be quantum computer that breaks cryptography. So here we are talking about 4,000 to 6,000 quantum bits with pretty good error correction on these bits to eliminate errors. So quantum chemistry is generally easier for quantum computers than breaking cryptography, because chemistry is naturally a quantum task. Breaking codes is not naturally a quantum task. So the number of quantum bits that one needs for breaking codes is about 2 to 3 times the length of the secret key. So if we are talking about encryption with 2,000 or 3,000 bit key, one would need 4,000 or 6,000 quantum bits for that. And I think this is still some time away. But there are considerations like this one. Historically, it has taken a long time from deciding that a cryptographic system is good until we actually get it out as a standard. This might take 10 to 20 years. And another consideration is that even if we don't have a quantum computer right now, some of our data needs to stay secure for very long times. It is plausible that a lot of data needs to stay secure for 10 or 20 years. So if we want something to be secure in 10 or 20 years, we should be starting to think about cryptography that is secure against quantum computers now. And that is starting to happen. There is a field of research called post-quantum cryptography that is concerned with making cryptography that would be secure against quantum computers. And this is a field of increasing interest. There's more and more conferences on post-quantum cryptography taking place. And the US National Institute of Standards and Technology is taking this seriously enough that they are preparing a contest for post-quantum cryptographic schemes with aim of coming up with some schemes that might be usable when the world has quantum computers. There are actually quite a few methods for post-quantum cryptography based on different mathematical problems. There are schemes based on mathematical objects called lattices. There are schemes based on error-correcting codes. There are schemes based on systems of multivariate quadratic equations. There's actually a lot of possibilities how one might be able to do cryptography that is secure against quantum computers. And some of these schemes have been around for a very long time. The oldest one of them dates back to 1978. And there are quite a few challenges involved in making these schemes practical. The basic challenge is that most of these schemes, they are actually families of schemes. Cryptography that is based on lattices or codes, one can base it on many different lattices or many different codes. So there are many different ways to do it. And in some cases, it's insecure. In some other cases, it's secure. Doing it in a simpler way makes the scheme more efficient, might damage security. So, for example, there is a very interesting cautionary story about a very efficient scheme that was discovered by British Secret Communications Headquarters, GCHQ. So they invented this very efficient scheme based on lattices, which they were going to propose as a candidate for quantum-safe cryptography. And then they discovered that the things that make this scheme very efficient also make it insecure. So there is a very subtle trade-off here between efficiency and security, and researchers are still working on that. So to conclude, and there are also some experiments of companies trying to put post-quantum cryptography into products. So there is this London startup called PQ Crypto, which stands for post-quantum crypto. So they are actually trying to sell post-quantum cryptography even now to organizations that want their data to be secure after quantum computers arrive. So this is what they have: post-quantum guard, quantum computer, and supercomputer resistant. And Google has also announced an experiment with post-quantum cryptography in their web browser. So what is happening, that a small fraction of Google Chrome users are having their information encrypted using a post-quantum scheme in an experiment to test the viability of these schemes. So post-quantum cryptography is moving along, and hopefully by the day when quantum computers arrive, it is ready. Yes, so to conclude, quantum technologies are moving towards being more practical. There are substantial advances, and it's time for scientists to start thinking about post-quantum cryptography, and that is actually happening. Thanks. If you have any questions, I'd be happy to answer them.
Well, if there is one question for Andris now, or you can ask it later in the break, It was very, very interesting presentation, and I think a lot to think for us, for more practitioners on everyday life. So, is there a question? No, there is. Okay, welcome.
Thank you for the wonderful speech. It was very interesting. My question is, what is the latest record for quantum bits? What is the maximum quantum bit achieved currently?
Maximum is 12.
12. Okay.
So what has happened is actually quite interesting. But the technology that is a front runner of quantum computing has changed 3 times. So first time 12 bits were achieved with one technology that didn't scale beyond that. Then it was achieved with second technology that was slightly better in scaling but still not as good. And now it's essentially achieved with third technology, with superconductors, which are quite promising in scaling towards larger numbers. So the number 12 actually has not changed in 10 years, but now we have a 12 with technology that might bring 100.
Thank you.
Okay. Thank you very much. Paldies, ļoti interesanti.
Paldies.